Welcome back to Chapter 3 of Principles of Mathematical Analysis. So far, we have built up a careful theory of numerical sequences, what it means for a sequence to converge, Cauchy sequences, upper and lower limits, and the 5 special limits collected in Theorem 320. In this section, we make the long-awaited turn to infinite series. We will define what it means to add infinitely many complex numbers, restate the Cauchy criterion in this new language, observe that the terms of a convergent series must tend to 0, and prove our first real convergence test, the comparison test. From here on, all sequences and series under consideration are complex valued, unless we explicitly say otherwise. Here is the plan for this section. We start with motivation. Why infinite sums show up everywhere, and what could go wrong if we are not careful. We then write down definition 3.21, which turns an infinite sum into a sequence of partial sums. With that in hand, the Cauchy criterion for sequences, Theorem 3.11, translates directly into Theorem 3.22. Cauchy criterion for series. A one-line consequence is Theorem 3.23. The terms of a convergent series must vanish. Theorem 3.24 specializes to non-negative term series, where convergence is the same as boundedness of the partial sums. We finish with the comparison test. Theorem 3.25, our first practical convergence test. Up to this point in the chapter, the basic object has been a sequence, an ordered list of numbers indexed by 1, 2, 3, and so on. We learned what it means for such a list to converge, what Cauchy sequences are, and how to compute several standard limits. But many of the most useful quantities in mathematics are not single numbers, and not just sequences either. They are infinite sums. The first expression on the slide is the geometric series 1 plus 1, half plus 1, quarter, and so on, which should equal 2. The second is the Leibniz alternating series for p over 4. These objects have been around since the dawn of calculus. There is a basic problem. The plus sign is a binary operation defined for 2 numbers at a time. Adding finitely many numbers extends without trouble, but adding infinitely many numbers is not a single operation we can perform. We need a precise definition of what an infinite sum even means. The classical idea, going back to Cauchy, is to reduce the problem to one we already understand. Instead of asking for the infinite sum directly, we form the partial sums. S sub 1 is just a sub 1. S sub 2 is a sub 1 plus a sub 2. S sub 3 is a sub 1 plus a sub 2 plus a sub 3, and so on. That gives a sequence of perfectly ordinary finite sums, and we ask whether this sequence converges. If it does, its limit is what we call the sum of the series. That is the definition we make precise next. Before we write the definition, one piece of bookkeeping. From this section onward, every sequence and every series in Chapter 3 is allowed to be complex valued. Whatever we prove about complex series automatically covers the real case as a special case. Extensions to vector-valued series in real k-dimensional space are pushed to exercise 15. Since they require nothing essentially new. Now to the definition. Definition 3.21 opens with a piece of notation we will lean on constantly. The capital sigma symbol shown on the slide bundles a finite sum of consecutive terms into one compact expression. A starting index p sits below, an ending index q sits above, and the dummy index nen runs over every integer in between, picking out the term a sub n each time and adding them together. 2 points are worth stressing. First, the notation is purely cosmetic. It stands for an ordinary finite sum and nothing more. Second, that finite sum interpretation is exactly why it matters. Once we let run off to infinity in a moment, the same symbol will pivot from shorthand into the central object of the section, the infinite series. Now the central definition. Starting from a sequence A sub n, we manufacture a brand new sequence by accumulating the terms one at a time. The n, the partial sum, written S sub n on the slide, is just the finite sum of the first n terms. Each S sub n is a perfectly ordinary finite sum. What is new is that we view them collectively as their own sequence. Then, in the second display, we introduce the symbol we will actually use for the rest of the chapter, capital sigma with n, running from 1 to infinity. The crucial point is what this symbol does not yet mean. At this stage, it is a symbol, not a number. It carries no value until we ask whether the partial sums it stands for actually converge. Giving the symbol a numerical meaning is the job of the next slide. Here is where the symbol acquires a meaning. If the sequence of partial sums S sub n converges to some number doshekes, we say the series converges, and we use the very same sigma notation to denote the limit S. This number -s is called the sum of the series. If the partial sums fail to converge, the series is said to diverge. The gray block underlines a point that confuses every student sooner or later. The sum of an infinite series is not obtained by addition. There is no last term to add. It is a limit of a sequence of finite sums. The same sigma symbol is doing double duty. On the left, it denotes the formal series. On the right, it denotes its limit, when that limit exists. 2 quick conventions, both shown on the slide. Some series naturally start at index 0 rather than 1, which is what the first bullet records. The choice is cosmetic, and we will switch between them freely. The second bullet says that when the starting index plays no role in an argument, we simply write capital sigma A sub n with no limits attached. The highlighted box at the bottom is the more substantive point. Sequences and series are really 2 views of the same data. Going one way, the partial sums of a series form a sequence by definition. Going the other way is just as easy. Given any sequence, take the first term and let each later term record the increment from one entry to the next. Then the partial sums of those increments recover the original sequence exactly. So every result about sequences can be reread as a result about series and vice versa. Both languages survive in the literature because each makes certain ideas easier to see than the other. A picture to make. Definition 3.21 concrete. The slide shows the partial sums of the geometric series 1 plus 1, half plus 1, quarter plus 1, eighth, and so on, plotted on the number line between 0 and 2. The dashed red line at 2 marks where these partial sums are heading. Reading the blue dots from the left, S sub 1 is 1, S sub 2 is 3 halves, S sub 3 is 7/4, S sub 4 is 15/8, and so on. Each partial sum lands exactly halfway between the previous 1 and 2. The amber arrow underneath captures the motion. The partial sums march steadily to the right, but never overshoot, closing in on 2. Since this sequence of partial sums converges to 2, definition 3.21 says that the series converges and that its sum is 2. The infinite sum is meaningful exactly because the sequence of finite sums has a limit. Theorem 322 is the Cauchy criterion translated into the language of series. Reading the displayed condition, for every positive epsilon there is an index n, past which every block sum, that is every consecutive piece of the series taken from index n up to index m, is at most epsilon in absolute value. The slogan version: every far-out chunk of the series is uniformly tiny. The reason this is such a powerful tool is in what it does not require. We can use it to prove convergence without ever knowing what the sum is. For almost every series we will meet after this section, there is no closed form for the sum. The Cauchy criterion is what lets us still say, yes, it converges in those cases. The idea behind the proof, recorded in the highlighted box, is simply to apply the Cauchy criterion for sequences, Theorem 3.11, to the sequence of partial sums. The next slide makes that translation concrete. The whole proof rests on one simple observation, sitting in the green proof block. Subtracting two partial sums collapses by telescoping. The shared terms cancel, and what is left is exactly the block sum, running from index n through index m. So a block sum of the original series is nothing other than a difference of partial sums in disguise. With that identity in hand, the highlighted box becomes a chain of equivalences. Bounding the block sum by epsilon is the same as bounding a difference of partial sums by epsilon. That bound, holding for all sufficiently large indices, is exactly the Cauchy condition on the sequence of partial sums. Theorem 3.11 then says a Cauchy sequence converges, and converging partial sums is precisely how we defined a convergent series. So Theorem 322 is not really a new theorem at all. It is Theorem 3.11 reread in series language. Theorem 323 is a free corollary of the Cauchy criterion. If a series converges, its terms must tend to zero. The intuition is easy to feel. If the terms refuse to shrink, every new term would knock the partial sum sideways by at least some fixed positive amount, and a sequence that keeps jumping by a fixed amount cannot settle down to a limit. The proof on the slide makes that intuition rigorous in one move. The Cauchy criterion gives us a uniform bound on every block sum from index n to index m. In particular, we are free to take m equal to n, in which case the block sum collapses to a single term, a sub n. The criterion now says that single term is at most epsilon in absolute value once n is large enough, which is exactly the definition of a sub n tending to zero. So the terms going to zero is necessary for convergence. The next slide warns that it is not enough. A vital warning. Theorem 323 is a one-way street. Having the terms tend to zero is necessary for convergence, but it is not sufficient. There exist series whose terms shrink to zero, and yet whose partial sums march off to infinity. Recognizing this distinction will save you from many false proofs. The standard counterexample is the harmonic series, 1 plus 1, half plus 1, third plus 1, fourth, and so on. The general term is 1 over n, which clearly goes to 0. Nevertheless, the series diverges. Its partial sums grow without bound. We will not prove the divergence here. It will follow as a special case of Theorem 328 in the next section on series of non-negative terms. The moral in the highlighted box is worth repeating. Knowing the terms tend to zero by itself tells you nothing about whether the sum is finite. The terms can tend to zero too slowly to be summable. This is why we need genuine convergence tests, and why the rest of the chapter is devoted to building them. Theorem 324 is the series analog of Theorem 3.14, the monotone convergence theorem for sequences. It is restricted to series of non-negative real terms. The footnote in Rudin emphasizes that non-negative always refers to real numbers, since there is no useful ordering on the complex plane. The reason is in the highlighted box. When every term sub n is non-negative, adding the next term can only push the partial sum up or leave it where it is. So the partial sums form a monotonically non-decreasing sequence. A monotonic sequence converges if and only if it is bounded by Theorem 3.14. Putting these together, convergence of the series is exactly boundedness of the partial sums. Here's the picture behind Theorem 3.24. The horizontal axis is the index n, marked with ticks at the whole numbers 1 through 10, to remind us that we are looking at a sequence, not a continuous function. The vertical axis is the value of the partial sum s sub en. The blue dots are the partial sums of a non-negative series, and the faint blue steps connecting them sketch the staircase shape. Because every term added is non-negative, each blue dot sits at or above the previous one, so the staircase only rises or holds steady, never falling. The red dashed line is an upper bound m. Every dot stays below it. The monotone convergence theorem for sequences then guarantees a finite limit, marked by the amber dashed line at s, and that limit sits at or below m. If no such m existed, the staircase would simply keep climbing and the series would diverge to plus infinity. So for a non-negative series, convergence is bounded staircase, divergence is unbounded staircase, nothing in between. Why is this so useful? Because for non-negative series, the qualitative question of convergence reduces to a single quantitative question. Are the partial sums bounded above by some fixed constant m? If yes, the series converges and its sum is at most m. If no, the partial sums are unbounded and, being non-decreasing, they march to plus infinity, so the series diverges. This reduction is what makes the comparison test, coming up in the next section, so effective. We no longer need to compute the sum exactly. We only need to bound the partial sums above by a series we already know is convergent. Hence the chapter's central strategy. Catalog a few known convergent series and use them as yardsticks. Theorem 325 is the comparison test. It comes in two halves. Part A is the convergence half. If, past some fixed index n sub 0, the absolute value of a sub n is dominated by a non-negative number c sub n, and the dominating series of c sub n converges, then the original series of a sub n converges as well. The terms a sub n themselves can be complex. Part B is the divergence half. If the terms a sub n are non-negative real numbers, and they dominate another non-negative sequence, d sub n, whose series diverges, then the larger series of a sub n diverges too. The gray caveat is important. Part B only makes sense for non-negative real terms. On to the proof of Part A. Fix any positive epsilon. Since the dominating series c sub n is assumed to converge, the Cauchy criterion for series, Theorem 322, gives an index n past which every block sum of c sub k is at most epsilon. We pick n large enough that it is also at least n sub 0, so that the hypothesis on the original a sub n is in force for every index from n onward. Now the estimate. Take any m, at least n, at least n. The chain of inequalities on the slide has 3 steps. First, the triangle inequality. The absolute value of a sum is at most the sum of the absolute values. Second, term by term, the hypothesis says the absolute value of A sub k is at most C sub k. So the sum of absolute values is dominated by the sum of C sub k. Third, by the choice of n from step 1. That sum of C sub k is at most epsilon. Putting the 3 inequalities together, the block sum of A sub k is at most epsilon in absolute value. That is the Cauchy criterion of Theorem 3.22, verified for the series of A sub n, with the same n that worked for the C sub n. So that series converges, and part A is proved. The highlighted box summarizes the pattern. We pushed the Cauchy property from the dominating series down to the dominated series, using only the triangle inequality and the term-by-term comparison. This kind of argument is the engine behind all the convergence tests that follow. Root, ratio, integral, and so on. They all amount to comparison with a series we already know. Part B is a free consequence of Part A. Suppose, for contradiction, that the larger series of A sub n did converge, since 0 is at most D sub n is at most A sub n past index n sub 0. Part A applied with C sub n equal to A sub n would force the dominated series of D sub n to converge too. That contradicts the assumption that D sub n diverges, so A sub n must also diverge. The gray box records an alternative, also pointed out in Rudin's text. Since the partial sums of D sub n are non-decreasing and unbounded, and the partial sums of A sub n dominate them term by term, those two are unbounded. By Theorem 3.24, the series of A sub n diverges. Either derivation works. The comparison test gives us a clear 2-step strategy for any new series. To prove convergence, bound the absolute values of the terms above by a series we already know converges. To prove divergence in the non-negative case, bound the terms below by a series we already know diverges. Of course, the test is only as good as the reference series we have on hand. The next section, Series of Non-Negative Terms, is devoted to building exactly that catalog. Geometric series, the so-called P-series, the Cauchy condensation test, and so on. Once we have those reference points, the comparison test handles a huge range of practical examples. Let us recap. Definition 3.1 is the foundation. An infinite series is, by definition, the limit of its sequence of partial sums. Convergence and divergence of the series are convergence and divergence of that sequence. The sum, when it exists, is a limit, not a finite addition. Theorem 3.22 is the Cauchy criterion for series, the direct translation of the Cauchy criterion for sequences. A series converges if and only if all sufficiently far. Tail blocks are small in absolute value. This is our master tool for convergence proofs that do not rely on knowing the sum. Theorem 3.23 is the cheapest necessary condition. If a series converges, its terms tend to 0. Equivalently, if the terms do not tend to 0, the series cannot converge. But beware, the converse is false. The harmonic series, with general term 1 over n, has terms that obviously go to 0, yet its partial sums march off to infinity. Vanishing terms are necessary for convergence, not sufficient. Theorem 3.24 specializes to series of non-negative real terms. There, the partial sums are monotonically non-decreasing. So by the monotone convergence theorem for sequences, convergence reduces to boundedness. This single observation turns convergence into a quantitative bound. Theorem 325, the comparison test, is our first genuine convergence test. Bound the absolute values of your terms by those of a series you know converges, and convergence transfers. Bound a non-negative series from below by one you know diverges, and divergence transfers. The whole proof is a one-line application of the triangle inequality and the Cauchy criterion. The big slogan to keep in mind, written on the last bullet, is that a series is its sequence of partial sums. Everything we proved here was really a theorem about sequences, dressed in series clothing. The conceptual leap is that this dressing matters. Thinking in terms of series organizes the material in a way that pure sequence language would not. Coming up next, we cash in on Theorem 3.25 by building the reference catalog it depends on. We will pin down the geometric series, the harmonic series, and the so-called p-series for various values of p, and we will prove the Cauchy condensation test, which links the convergence of a series to that of a sparse subseries. With those reference series in hand, the comparison test becomes a powerful, practical convergence tool. See you in the next section.